Welcome to my talk in database machine learning with SQL on GPUs. The motivation for this was like, how does a fully automated data pipeline looks like? Often it is a giant house of cards built from random scripts that will all completely collapse the moment any input does anything weird. So what's the answer as a solution of using a lot of random scripts? I say the answer is use SQL. So this talk claims that SQL is sufficient for machine learning. SQL is Turing complete with recursive tables. Our SQL in Umbra supports streams for continuous learning, and we have a sample operator for stochastic gradient descent. So our idea is, why don't do data pre-processing using SQL? This means no need for data extraction out of a database system. Then we can continuously train a model using operators for gradient descent and maybe add GPU support. Afterwards, we can label data within the database system using SQL. The structure of this talk is as follows. First, we will present machine learning using bare SQL 92. So, more precisely, we show gradient descent with recursive tables and a machine learning pipeline in SQL. Then we continue with machine learning operators for Umbra. Namely, we present automatic differentiation as an operator as well as gradient descent as an operator. Afterwards, we add GPU support to our operators by enabling GPU coprocessing, and we present the evaluation of our research. Let's start with machine learning in SQL. So, how does gradient descent looks like? We have a loss function, and this loss function we need to take the gradient. Then in each iteration we subtract the gradient times the learning rate, and finally we will get the optimal weights. This can be expressed using recursive SQL. First, as the base case, we need the initial weights. Then, in each iteration, we need to update the weights. And finally, after a certain number of iterations, in this case 5, we can gain the optimal weights. So this is batch gradient descent using recursive tables. Then, instead of using the whole batch, we only can use one tuple. Using our table sample operator, we just pick one tuple, and this then is gradient descent, stochastic gradient descent. We can increase the size of a batch and take a mini batch, for example 8 tuples per iteration. And now we have mini batch gradient descent, all using SQL 92. Then, what are the components of a machine learning pipeline? For example, at EDBT, the following components have been proposed. First, we need an input parser to pass input as CSV files. Then we have a feature extractor to extract the features we are interested in. Then we want to filter out some anomalies. An anomaly occurs when at least one attribute in a tuple passes over or under a predefined threshold. Then we want to scale each attribute on a range between 0 and 1 to equal each attribute's impact on the model. And afterwards, we want to manage gradient descent. And I say that these components can be done in SQL. For example, in relational form, the input parser is just a simple table scan operator. Or if you want to do continuous machine learning, we can use our recently introduced continuous views. Then for the feature extractor, this means a simple projection to the attributes we are interested in. And other things like the distance matrix can be calculated using arithmetic operations. Afterwards, we can filter out anomalies using a projection. And then the standard scalar can also be done using a projection with nested queries to extract the extrema. Then we need something to do gradient descent, like the proposed recursive tables I have shown in the last slide, and afterwards we get the optimal rates. So this is the form in relational algebra. And now, how does it look in SQL? It looks pretty brilliant. So we have first our grade for a table for starting our continuous view. Then we insert the data. Then we create some views for processing and normalizing the data. And afterwards, we can see one big recursive table to gain the optimal weights. But if you say, okay, 6 lines, can we compress that? I can say, of course we can. But what do we need there? We need a new operator. So that's where we came up with Umbra operators. The first operator uses lambda functions. So first of all, what are lambda functions? We have dedicated operators, we have SQL, we have user-defined functions, and we have external tools. So within our database system, operators are quite performant. SQL offers us a good performance, and it's better than UDFs or even external tools, but UDF and external tools are quite more expressive. So the solution is lambda functions to customize use operators, hard-coded operators for user-defined purposes. So lambda functions in Umbra and Hyper are provided for example, k-means or PageRank. So Hyper and Umbra are code-generating database systems which produce LLVM IR, intermediate representation code. Then lambda expressions are used to inject code into regular operators. And how does a lambda expression look like? We have lambda arguments to identify the tuples, and we have a lambda body to formulate an expression as regular SQL expression. For example, using 2 tuples, we can inject a distance metric like Euclidean distance inside of a k-means table operator. So we have data points and center points for the initial centers, and then we can inject Euclidean distance function, but also we could inject another distance function. Okay, so these lambda functions are now used for automatic differentiation. So what is automatic differentiation? Automatic differentiation using backward mode means applying the chain rule top-down to backpropagate the loss. This has the advantage that there is no need for manually deriving gradients. And in our implementations, we can cache sub-expressions in LLVM registers for reuse. So this is a function composed of another function with 2 inputs. And how does backpropagation work? First, a value is backpropagated, and then by applying the chain rule, we can backpropagate the loss. And this will be exposed as an SQL operator inside Umbra to enable automatic differentiation within SQL functions. So for an example, I've created this function x plus y times z. So at first we have to calculate the result. The result is 30. Then we start with an initial loss 1, and then we backpropagate the loss to the sub-expressions. And finally, we get for each variable the value of its derived value. For x, it's 6. For y, it's also 6. And for z, it's 5. It's also the result of our operator. Using this operator, we can see that manually derived, we have to hand derive the gradient. But using our derivation operator, we only have to call it. We do not have to calculate the gradients by hand. And using this operator, we can also train a feed-forward neural network. A feed-forward neural network is composed of matrix multiplications plus an activation function. And the forward pass just means multiplicating it, and afterwards we can subtract the loss and using also least squared error for the loss. So within our recursive tables, we need array operations. So at first, we create the initial weights, having one matrix and another matrix, and then we perform iterations of gradient descent. And here you can see we just enter the loss function shown here in equation 7, and then we can apply gradient descent also to a neural network. So to further facilitate the usage of gradient descent and also to allow to be able to offload it to a GPU, we present gradient descent as an operator. So as an operator, we also need the lambda functions for automatic differentiation. And how does our operator look like? We need a binary operator with one input for the training data and one for the initial weights. And we also need the loss function. And afterwards, we produce the optimal weights that can be used for another operator like labeling, where we label test data. And this gradient descent operator allows us to call specialized libraries and offload to GPU. That's the next topic in our talk, GPU coprocessing. So GPU coprocessing has to take into account the GPU architecture. Each GPU device owns one global memory, the device memory, and an L2 cache. The core components of a GPU are streaming multiprocessors with an attached shared memory. Inside of such a streaming multiprocessor, parallel threads perform the same instructions simultaneously. At least 32 threads are possible. 32 threads in a bundle are called a warp, and multiple warps, so at least 32 threads, form a block. And the challenge of this talk is now to map the mini-batches from gradient descent to the blocks in our GPU. So at least one mini-batch must contain 32 threads. And what can we vary? We can vary the number of warps per block. So, therefore, we propose multiple learners per GPU. So the goal is to utilize all GPU threads even with small batch sizes. So the solution is we have multiple independent learners at block size granularity. That means each block corresponds to one learner, and one learner is responsible for a batch. Each learner maintains its own independent local weights, W local, and it also maintains the differences C to the global weights, W. And as I said, we need at least one warp within a block, so the minimum batch size here is now one warp with 32 threads. And the maximum number of learners we can allow is the maximum number of possible warps can be processed on a GPU. So now we have independent learners. So this means we need to synchronize them. So there are three possibilities of synchronizing weights. The first is synchronized threads. We first let every learner compute its gradient, then it waits, and then we have to update global weights. Another possibility are worker threads with global updates. So independently, each worker can continue his work because he does not wait for another one and updates the weights. But there's the problem that we need locks, ether locks, which would hinder slower GPU units or slower devices from their work, or we omit locks and take into account some small computation errors. So the third solution are worker threads with local models. Local models are known from Crossbow. Each learner maintains local weights, and for every learner, a vector called correction stores the differences to the global weights. After each iteration, the corrections of all learners are summed up to form the global weights. So that's what we propose also for our GPU learners on a smaller granularity. So Crossbow is doing the granularity in big learners and so on software computed learners, and what we do is on a hardware granularity, because we take into account the warps. We have one warp per learner, or better saying one block per learner. So let's come to the evaluation. First of all, the setup. We have Intel Xeon Gold processors with 14 CPUs per NUMA core, and we were running on a Ubuntu machine 24 with 256 GB of RAM. We trained either on 4 GPUs. We compared NVIDIA GTX 10080 Titanium or RTX 2080 Titanium, or we were using one NVIDIA Tesla V100. As models, we used linear regression and a feed-forward neural network with a single hidden layer for image recognition. And as data, we used synthetic data and the New York Taxi dataset 1 month from January 2015, and we're using MNIST as well as the fashion MNIST dataset for image recognition. Let's come first to automatically versus manually derived. So automatically using our Umbro derivation operator versus specifying each expression per hand using another SQL expression. What did we perform? We did perform batch gradient descent using synthetic data on a linear model. And what we can see is that automatic differentiation speeds up compilation time and execution time. So we have here, we can see the compilation time, which is of course quite smaller than executing our program, our SQL queries. And we can see that manually deriving needs a lot of more time as for the compilation time as well as for the execution time. So 3 different cases. We have recursive tables as proposed with either manually or automatically derived gradients, and also we compared our dedicated single-threaded operator. What is also visible when the batch size, so yeah, this performance difference, so that manually derived operators are performed worse than automatically derived gradients, is also visible when we vary the batch size, the number of iterations, or the number of threads. What we can see is that using our recursive tables, this scales, as unfortunately our GPU, our operator, which does not offload to GPU, so it's just a simple operator for performance measurements, for comparison, that only works on CPU, not parallelized, does not parallelize, of course. So, but what we can see is using SQL, it automatically parallelizes. So the gain of this function is automatically deriving a gradient speeds up the compilation of gradient descent. So now we compare the different GPUs for GPU coprocessing. In this case, we compare the performance of multiple learners. So what did we do? We varied the number of threads per block. So the minimum block size of at least 1 warp, 32 to 1024 threads. And we are using 4 attributes for this experiment. Also, we varied the number of attributes. As we can see, the throughput slows down the more attributes we have. The highest throughput is achieved when the batch size is a multiple of the block size. So we can see here the spikes. And the local maximum spikes are when the batch size is a multiple of a block size. So, but what is the takeaway of this slide? The takeaway of this slide is that with our learners, we can fully utilize a GPU because we have small mini batches to train. So what about the parallelization to multiple GPU? So we compared different synchronization models, so either no synchronization using global updates without locking, then local models with either locking or not locking the critical section. What we can see on the CPU, of course, we have a linear speed up, and of course global updates do not slow down any other workers, so this achieved the best performance. With locks, we have a lower throughput as blocking threads cause underutilization. On GPU, we can see the same. The larger the batch size, we need less synchronization, so the higher is the scale up, as parallel workers work independently. With local models, the GPU communication, the inter-GPU communication decreases the performance. So as we can see, the second GPU increases the throughput, the third also, and the fourth not as heavily as adding the second one. We did the same also for the neural network. One additional worker increased the throughput. For any further workers, the inter-GPU communication decreased to runtime. For small batch sizes, the best result was when we used 2 GPU devices so here on the left, but the larger the batch size is, so on the right, every additional device allowed a higher throughput. As you can see, it scaled up. Finally, I want to show you end-to-end testing. So we trained one epoch of a New York taxi dataset. We built our machine learning pipeline in Python using Keras and in SQL in Umbra. So what are the steps? The steps are data loading from CSV, feature extraction, normalization, and then trained the model. So as we can see, much time was spent on loading, and this step is simply not required if we store the data anyway in the database system. Other steps like extraction or normalization is quite faster within the database system. And what we can see is training with recursive tables is already slower than using Python with Keras. So our recursive tables, even when the manually derivations are used, is faster. And then of course our GPU co-processing is quite the fastest. So it was all outperformed by our operator that offloads training to GPU. To conclude, we have expressed our in-database machine learning pipeline in pure SQL based on sampling, continuous views, and recursive tables. We proposed one operator for automatic differentiation and one for gradient descent. We offloaded training to GPU units, and we trained algorithms as GPU kernels and fine-tuned learners at hardware level to increase the learning throughput. Automatic differentiation accelerated both the compile time and the execution time by the number of cached expressions. Fine-tuned learners at hardware level allowed the highest possible throughput for small batch sizes. Finally, end-to-end machine learning pipeline in SQL showed comparable performance to traditional machine learning frameworks. And by that, I thank you for your attention.